Welcome to this explainer. Today we are unpacking the incredibly dense bare metal mechanics of the consensus hypervisor. We're going to explore a really fascinating paradigm shift, how this architecture literally transforms chaotic probabilistic states into an ordered, rock-solid reality right at the silicon level. It's a wild journey from high-level mathematical theory all the way down to the physical execution pipelines.
Here is our structural roadmap for today. Working top-down. 1. Chaos to ordered consensus. 2. Payload resonance and mutation. 3. Predictive pipelines. 4. Memory fencing contrast. 5. Preemptive paging. And finally 6. Spoofing IMMU faults.
So you might be wondering, how exactly does a hypervisor build an ordered ghost city out of sheer mathematical chaos? Well, to really grasp this, we have to understand how the consensus architecture moves completely away from rigid static hardware mapping. Instead, it starts treating data states and memory addresses as emergent phenomena. Basically, these things only materialize when the precise cryptographic conditions are met.
Let's start with part 1, chaos to ordered consensus, and balancing that entropy.
If you're an engineer, you know that turning chaotic, encrypted data into a sovereign, ordered state usually creates massive performance bottlenecks and heavy CPU loads. It's normally where a system is most vulnerable. But here is the crucial point. Instead of forcing immediate entanglement, which would absolutely lock up the processor, this system uses something called chaos thresholding. It implements a phase transition model. Think of it like a pressure valve that actively waits for a critical mass of entropy to build up before it collapses the data into an ordered consensus. By treating data as differential energy and pacing out its convergence, the hypervisor completely smooths out those nasty processor spikes.
Moving right along to part 2, payload, resonance, and mutation. This is where the data literally routes itself.
To pull off true generational emergence, the hypervisor completely ditches classic static memory addressing. The data doesn't just sit where it's told anymore, it routes itself. This happens through address bit dynamicism. By relying on the payload's own cryptographic resonance to dictate the next hop, the data's route becomes completely entangled with the file itself. It forms a state-dependent topology, so if even a single bit of data changes in one level, the addresses for all the following levels shift entirely. It is physically impossible to map a route without the exact mathematical frequency of that specific payload.
And the mathematical relationship here is honestly brilliant. Instead of relying on heavy software logic, the hypervisor just XORs the static address bits with the top bits of the current payload. That's it. This creates dynamic, mutating routes with 0 extra CPU cycles. The entire route calculation is executed natively right in the hardware vector registers. It's incredibly fast, and more importantly, it's cryptographically sovereign.
All right, part 3, predictive pipelines. Let's talk about the Scout and the Guard.
So the goal is zero wait state projection, right? The guest operating system should never even realize that the memory it's accessing is being mathematically generated on the fly. To make sense of this lock-free design, let's use a simple analogy. Think of Core 0 as the fast-moving Scout, the address engine. It's out there navigating those 10-bit routes and projecting probable paths directly into the cache. Then you have Core 1. Core 1 is your heavy-duty security guard, the frame controller. It trails behind asynchronously, just verifying the sovereign cryptographic hashes. If the guard spots a mismatch or any kind of injection, boom, it instantly triggers an interprocessor interrupt. This rolls the state machine back and completely evaporates that malicious data.
Which brings us to part 4, memory fencing contrast and the reality of silicon differences.
Now, all this beautiful theoretical logic doesn't mean much on bare metal if we ignore cross-architecture differences. Determinism is absolutely vital here. The x86 architecture uses a strong memory model, whereas ARM hardware uses a weak memory model. Because ARM allows for much more aggressive instruction reordering, cross-architecture pace expansion can quickly cause your projected storage to just completely desync from your projected RAM if you aren't careful. And standard C++ atomic models, they simply aren't enough to handle this. So to fix this bare metal synchronization issue, the hypervisor surgically injects specific inline assembly barriers. We're talking about instructions that explicitly enforce strict hardware-level memory ordering. They guarantee, without a doubt, that the Scout's speculative writes are physically flushed to the bus before the frame controller ever even attempts to verify a speculative route. Okay, part 5, preemptive paging. This is where we harvest idle CPU cycles. Because here's the thing. Even with perfect memory fences, deterministic projection can still cause stuttering during high-entropy writes. So, to effectively mask that MMU mapping latency from the guest operating system, the hypervisor grabs exactly 128 available cycle hints to ensure zero-wait state data delivery. But you might be asking, where exactly do these cycles come from? Well, they're harvested directly from the guest OS itself.
It's pretty clever. When the guest OS thinks it's taking a rest, like executing a halt or wait for interrupt command, the hypervisor intercepts that exit. Instead of letting the CPU sleep, it redirects those dead execution cycles over to the arithmetic logic unit. It uses that free time to pre-calculate the upcoming mathematical emergence of the next sector. By the time the guest wakes up and asks for the data, it is already collapsed and waiting right there in the L1 cache.
And finally, Part 6, spoofing IOMU faults to achieve true hardware invisibility. We've hit the absolute lowest level of hardware constraints here. Think about it. If data suddenly starts routing itself chaotically, modern silicon gets very, very suspicious. Hardware today expects strict, static memory access boundaries. If the IOMU controller spots emergent routing, it will instantly throw a security exception. To stop that from happening, the hypervisor acts as an active camouflage layer. It natively spoofs isolation faults just to keep the data moving seamlessly. And the timeline of how that camouflage works is staggering. Within just 25 nanoseconds, the hypervisor catches the fault, calculates the dynamic route on the fly, and seamlessly patches the page table. Then it issues a hardware-level resume command. Both the physical hardware bus and the guest OS remain completely unaware that any intervention ever even happened. Which leaves us with a truly fascinating paradigm shift to wrap up this explainer. If you have a perfectly ordered consensus architecture, malicious data isn't just blocked by some software firewall, it literally lacks the mathematical frequency to exist in the first place. If an attacker doesn't possess the precise resonant key, their exploit is mathematically invisible noise. It really forces us to ask, are we looking at the end of the zero-day exploit entirely? Think about that, and thanks for exploring this bare metal reality with me.